I'm Xiyue Liu. I'm a postdoc from National University of Singapore. And today I'm going to share with you my research work on the chemical signals behind the synchronized locust outbreak risk. So the desert locust is considered as one of the most dangerous migratory pests in the world due to its high mobility and fast breeding speed. And a swarm of 1 square kilometer can comprise 80 million locusts and consume as much food crop in a day as is sufficient to feed 35,000 people. This hazard of desert locusts have been known for centuries, so why do we still aim to study them? You might have heard of the severe locust crisis during 2019 to 2021, which was the worst in 30 years in Kenya and 20 plus years in the other countries. Such large-scale locust outbreaks simultaneously invaded several countries, strained the shared international locust control resources, and disproportionately burdened the control system of local organizations. This kind of phenomena is not by accident. There are physical mechanisms behind such kind of large-scale infestation. For example, the spatial gathering of desert locusts due to the localized extreme rainfall over multiple places will enforce the desert locust to concentrate in a very small area, and this can lead to gregarization, which is a reverse transition process from solitarious to gregarious phase in response to a marked increase in locust numbers. Such gregarization can largely increase the locust mobility and lead to the formation of hopper bands and adult swarms. So this kind of compound risk is overlooked in previous literature. Besides, previous literature often focused on the time series or the spatial or very limited geospatial locations. And in this study, we aim to disentangle the complex locust spatial temporal dynamics linked to the climate and investigate the continental scale locust dynamics. Besides, we are probably the first one to ever quantify the compound risk of such spatially synchronized locust occurrence. The dataset we are using here is the locust hub, which documented the occurrence, the observation of locust in different locations, and is documented by FAO from UN. The period we use is from 1985 to 2020. And the climate dataset we analyzed is ERE5 reanalysis and the global drought and flood category. The data-driven method we use here is the dynamic mood decomposition, which was first developed for the fluid mechanics to extract some spatial temporal patterns with very low computational burden. For example, a walking person here, it can be decomposed into the jumping mood, translation mood, and the walking mood. As a simple exploratory analysis, we first look at the time series and the spatial distribution of locust outbreaks. We found that there are 10 hotspot countries accounting for more than 4/5 of the total locust outbreaks during 1985 to 2020. Those countries are located in the Northwest Africa, the transition zone, East Africa, the Middle East, and the Indo-Pakistan region. We also found that the locust favors arid and hyper-arid areas, that is, such light green area. Using the DMD technique, we can extract the spatial temporal dynamics from locust outbreaks. Here we look at the 1-year periodic mood extracted from such locust outbreaks. The magnitude, it shows the level of participation for each geospatial location in the whole locust dynamics. It can help us to identify the hotspots. For example, the 10 hotspot countries account for more than 76% of the magnitude for the entire study area. And we can also compute the phase for our extracted mood. This phase, it measures the peak time of locust infestation for particular locations relative to the others. So we can use it to interpret the spread of locust outbreaks across the region. For example, you can see some migration pathways along the Northwest Africa coastal area and migrate southward along the East African and northward along the Red Sea coastal area. Such migration pathway is consistent with previous literature on the locust breeding belt and also their migration ways. It also shows the entomological connectedness. For example, the transition zone area, it all have similar face colors, which means those areas tend to encounter the locust outbreaks in similar times. And based on the phase, we can further quantify the compound locust risk. For example, the inter-country compound risk is measured by the median phase difference between country A and country B. And the intra-country compound risk is measured by the interquartile range for within one particular country. In this figure, we show such quantified compound locust risk in a chord diagram. Such green ribbons, it shows the inter-country compound risk or the phase difference between country pairs. The singer side is the lagging country and the seeker side is the leading country. For example, the Niger and Mauritania here, you can see my mouse, right? The Niger and the Mauritania, they face very high compound risk. And the Niger is the country that tend to encounter locust outbreaks first, and then Mauritania face the peak locust outbreaks. And the green nodes, it shows the intra-country compound risk. The green nodes show the intra-country compound risk, or the phase range within a country. We quantify such compound locust risks during the first half period, 1985 to 2002, and the second half period, and we compare the difference between the two periods. We found that about 1/5 of country pairs face high inter-country compound locust risk. For such high compound risk, we are measuring the compound risk within a 1-month time window. And many long-distance countries have seen an increase in inter-country compound locust risk, such as Pakistan and Morocco, if we compare the second half with the first half period. And we also found during those two periods, the intra-country compound locust risk hasn't changed much except some particular countries. We also quantify the climate locust relationships using the correlation of DMD magnitude between climate variables. Those are 5 climate variables and the desert locust. Still, we compute for the first half period, second half, and the difference between the first and second one. We found a strong correlation between the precipitation anomaly, air temperature, and wind speed with locust outbreaks dynamics. Such kind of physical factors are also the ones that determine locust life cycle, such as egg incubation, hopper development, and flying. Additionally, we found that the inundation has become increasingly important since 2003. This implies that arid areas affected by extreme rainfall are becoming more likely to induce locust outbreaks. We further use the multi-resolution DMD to investigate the impact of some climate variability on locust outbreaks. The major advantage of MRDMD is that it can extract the modes subject to a finer temporal resolution. For example, here we can specifically extract the background mood for La Nina years or the background mood for El Nino years. With this, we extract those separately. And then we summarize for all the El Nino years and the La Nina years. We find that for El Nino years, it has a larger contributing area to the locust dynamics, 65% larger than the La Nina years. And also, if we compare their difference, we find that the El Nino years show dominated locust dynamics over the East Africa and the Middle East, likely due to the above average rainfall in southern Red Sea and the Horn of Africa, while the La Nina years tend to show high locust dynamics over North Africa and the transition zone area, likely due to the excessive rains in the northern Sahel. We further predict locust distribution during historical and future SSP 126 and 585 scenarios using multi-model ensemble climate projection and the species distribution model. We found that there is a 5% increase in locust habitat area under SSP 126 and 13 to 25% under the SSP 585 scenario. There are also new hotspots found in the West Central Asian and the West Indian area, notably under such SSP 585 scenario. Overall, the centroid of locust habitat is likely to shift northward by about 0.3 to 1.2 degrees. Okay, now let's come to a brief summary of today's webinar. In this research, we analyze the spatially synchronized locust risk and the locust climate relationships. We find that the spatial prevalence of locusts is modulated by climate variability, such as El Nino sudden oscillation. We also find that a warming climate will lead to a widespread increases in locust outbreaks, with emerging hotspots in West Central Asia, posing additional challenges to such global coordination of locust control. Our paper has been published on Science Advances, and there are some social medias reporting this. If you are interested, feel free to read our paper stated below, and I welcome any questions from you.